see, this is just for today. Today only the class duration is for 1 hour. Otherwise, it will be your usual class. So see, this is the chapter 2 of your electrostatics. This is still a topic of your electrostatics. Means your charges still have not started moving. When a charge is static, what all things can occur? Like electric field was a concept when your source charge is put stationary. What all phenomena can occur beside? So that's what we study under the heading of electrostatics. So your first chapter is done. In your second chapter, you have the concept of potential and capacitance that is also considered under your electrostatics. Electric potential is mainly your electrostatic parts, which will end till the energy. So finally, your energy component and most of the things will be introduced in this chapter only. And one blessing is there that all these quantities are scalars. So this helps in making the calculations very easier. So electric potential and capacitance. Now, first you need to understand what is meant by electric potential. Okay, before even understanding what is the definition of this electric potential, you need to understand what is meant by electrical potential difference. First, let us see what is meant by a potential difference. Now, see Ibrahim, if I have a charge present, let's say that there are 2 points. This is B point and this is A point. Now, what I am doing, I have a charge present, this small, and this is point A. I am shifting this small q to this A point. Means I am bringing this small q to this A point. This here in the whole process, I am doing some external work, right? Some external forces are there. For me, I am the external force for the system. So external force is making the charge move in a direction. So when you have the charge present, Q charge is present and this is moving in a direction because we have made it. So basically there's an external force that is occurring in your system. Now, when you are moving something from one point to another point, a displacement also occurs. So displacement is also there. Now, when you have force, when you have displacement, what's the quantity that comes in action? Work done, right? So here, basically, whatever is the work done in order to bring this charge from B point to A point is referred to as the potential difference. Whatever is the work done in bringing this small q from point B to point A is called the potential difference. Whatever you are doing the work, why is the work being done? Because there is some external force in your system, which is bringing the charge to a point. Got it?
Yes, ma'am. Yes, yes.
So when this is present, when you have one charge present at B point and you're bringing it to a point that is A point, whatever is the total work done on this charge, done by this charge, because there is a force, there is a displacement covered, we call this work done for this charge as the potential difference. Now, for understanding the whole concept of potential difference, one thing you should already be aware of is the work done concept from your class 11. In class 11, we discussed that work done is F dot S. F dot S means F is the force, S is the displacement. So it is F S cos theta when the displacement is constant, force is constant. More than the displacement, force is constant. But if your force is variable, you integrate it from some x1 to x2 value like this, F dot dx, you integrate it from x1 to x2. So this is what is required from your class 11 to do. So what happened here? We just brought a charge, a test charge is there, a small charge is there, which we means according to the system, this is the external force, which is bringing the charge from B point to A point, means one point to another point, that's it. And whatever is the work done in this process for bringing this test charge, we have recorded. And that is what is known as the potential difference. Now understand what is an electric potential. If this is the electrical potential difference, but we are not focusing on difference, what is this different? What is this electrical potential? So see, Ibrahim and Jesslyn, if I make one charge from where I was getting the charge, that B point. If I shift that B point to infinity, I'm just shifting it far away, far away, far away, and I have shifted that point to infinity. This is the B point. Now, means it is infinity. So B point is actually no more, you just have this infinity present. And here you have got your charge. From here, there is one point A. A point is still there in your system. You are bringing this charge from infinity to this point A. It means what are you doing? From infinity, you are bringing this charge to this point A. In the previous case, what did we do? We just took charge from one point to another. And whatever work done was there, we recorded. Now what are we seeing? That when the charge is moving from infinity, this is very important, it's moving from infinity. So what will happen when the charge is moving from infinity to a particular point? Again, there will be force external. Again, there will be a displacement produced. So you will again have a work done in your system. Now this work done in bringing a unit positive test charge from infinity to that point is what is called as electric potential. When you are just bringing charges from one point to another, that work done per unit charge is electric potential difference. But when we are bringing the charge from infinity to a particular point, that is called as electric potential. So basically, it's all about the work done. Now, let us see. First, tell me, these two meanings are clear, the basic meanings.
Yes, ma'am. Yes.
Okay. So see, now you can understand, you have studied electric field. In electric field, we saw that when you are bringing a test charge around a source charge, you experience electrical properties and everything. Now class, electric field was completely based on your vector quantity. Your vectors were involved there throughout that chapter. Your scalar form of the electrical properties is what is given by potential. Potential is not the vector form. It's the scalar form in which the electrical properties are experienced. So it defines electrical properties around the charge in a scalar form. And it's also a property of single charge like your electric field. If one charge is present around it, there will be an existing electric potential, right? So this is a property of a single charge. Now, when you are talking about the potential, now let's look at this first, electric potential. So when you are calculating the potential here, so potential is work done in bringing a charge from infinity to a point. Work done per unit positive test charge. What is this? This is unit positive test charge. You're just bringing a unit positive test charge, and whatever is the work done is equal to your potential. So work done in bringing charge from infinity to point A is the potential. Now, when you're talking about the definition of potential, this is what it was. This is the exact definition of potential that you should know. So when you're talking, okay, you can relate it like this. See, this is work done by charge. See, when we discussed electric field in that chapter, if you remember, electric field was equal to force per unit charge. Remember, there was this formula, electric field is force per unit charge. Yeah?
Yes, ma'am.
So see, similarly, potential is work done by charge. See, electric field was a vector, force was a vector, so you got the answer also vector, right? E is equal to F by Q. Here it is depending on work done, not the forces. So work done are scalar quantities, hence the potential is also a scalar. So what do we write as the complete definition? It is the work done in carrying a unit positive test charge from infinity to a point against electric field and without acceleration. So what's the SI unit for it? What's the, see, it's a scalar quantity. Second, SI unit. This is electric potential. So straight away you have a very common unit, that is voltage. This voltage V is the SI unit. So what all things are there? What did we study? Just summarizing it. When you have the electrical properties scalar form, it is called as potential. What is potential difference? When a charge is brought from one point to another point, whatever is the work done against the electrical forces, we call it as electric potential difference. But if the charge is brought from infinity to that particular point against electric field and without acceleration, then we will say this is electric potential, whose formula for a point charge we will see, but this is the basic definition. Is that clear to both of you, Jasleen, Ibrahim?
Yes, ma'am. Yes, yes.
Okay, and Jasleen also is it's clear. Okay. Please start writing from here. Just text me done in the chat box so I'll scroll it. Class done till here?
Yes, ma'am.
Okay, Justin, what about you? Done? Okay. So see, now let us see what is the electric potential for a point charge. Now to calculate this electric potential for a point charge, see, your integration should be fine for this chapter. So class, if you have forgotten your integration portion, just refer to your class notes, or if you want to arrange the class, then let me know. Because in this chapter from here, your integration will start. Okay, integration, differentiation, both of it will start. Now, potential for a point charge is, see, we discussed that this external force is bringing this charge at this point and on. So when you are calculating force can never be calculated alone. You require this one more charge to exist. So that's why what are we doing? We are having one more charge present, and at a point we are trying to bring this charge from infinity to this particular point. Okay, like this charge, we are carrying this charge, and this charge we are trying to bring it at this particular point. Now this is our, this particular point that we are taking, this is our, and let's say this separation. So you are trying to bring the charge from infinity to r, right? This distance is what? This distance is r. So you are trying to bring a charge from infinity to this distance r. And whatever is the work done in this process, that is your potential. This is what we are trying to do. So for that purpose, we just had this charge present. See, this charge small q is present, and we are trying to bring it to this point. This is from your infinity. This is at your infinity. This charge is present at your infinity. And there is an external force experienced by it. Now, before we start with anything, class, when we talk about the Coulomb's law, this is capital Q, this is small q. So when you have the full formula for the electrical force from your Coulomb's law, can you tell me what will be the force between both capital Q and small q? Forces should be clear by now to all of you. Yeah, what's the force between capital Q and small q?
Ma'am, KQ by R square.
Yes. By not r square. Charge is not here. Where is the charge right now? At this some x distance. Okay.
Oh, okay.
We are keeping the
KQ by.
charge right now at some x distance. X distance means till this infinity, there is some x distance. And we are trying to bring it from infinity to this a point, and this a point is separated by capital Q by r distance. Basically, what is happening? You have the small q, you are trying to get it at a point A. So what is this A point? A point is a random point that is taken from plus q, so that you can calculate the potential. At plus q, you're not calculating. But why did we require this plus q? Because we want force in our system. So as Ibrahim correctly answered, the force will be K capital Q small q divided by x square. This is the force experienced. This is the value of the force. Force when it is at infinity, and you are bringing this from infinity to this point. Basically, this is the whole path that it has to travel. And we have taken the separation from the plus q also as r. Now this is what we have. One more thing, when we are talking about the displacement, let's assume, see, this is the force according to the Coulomb's law. Correct. This is the force according to the Coulomb's law. Now let's assume that I have chosen a very small, minute displacement in between, a very small displacement. Let's say dx. Dx is the displacement of small q. Okay, from infinity to this point r. A very small displacement I have taken. Now class, if I integrate it from infinity to r, right, from this infinity to this point r, I'll get the exact length and formula and everything, whatever I need. So what we do, since we have force, since we have displacement, and we studied also that potential is entirely based on work done. Our work done, when you combine this, work done will be simply F dot dx which will be K capital Q small q by x square dx. Now, how will we get our answer? How will we get the value of work done? You integrate it. So when you integrate this, when you put the value, you get the value as K capital Q small q by x square dx. This is work done, but from where are you integrating it? From some infinity point to a particular point A that is separated by R. Means from infinity, you are bringing it to R, infinity to R. Now class, see if I take K capital Q small q common from here, I'm taking this common. Okay, one more thing class. This is the force not done by the external. See, one more thing. If I have this, so if I have this F is equal to K capital Q by X square, this is the Coulomb's law. Class, this is the force that is experienced by this small q. Now, there is a force that is acting, which is the external force, and there is a force which is acting within the system. So this, Ibrahim, the force that you told me was within the system only, no, between capital Q and small q, between the system, right? So what do you do? For the external force, you have to put a negative sign. See, due to action reaction, F is minus F external. So F external will be minus K capital Q small q by x square. So we have to put a negative sign to show that it is the external force. Okay, if it was, see, the force that is within our system is F, which is K capital Q small q by x square. The force, external force that is present will be minus. So we'll just have to put this minus sign. Okay, one minus sign. So now, what is there? Minus K capital Q small q 1 by x square, integrating it from infinity to R. This is how you are integrating it, dx. Now, to integrate this, bring it in the numerator. Minus K capital Q small q, x to the power minus 2 dx, integrating it from infinity to R. Now, what is the next step? If you have x to the power minus 2, K minus K capital Q, this is outside. X to the power minus 2, what it has to be written as? Jesslyn, you tell me. On integration, x to the power minus 2. What's the next step that we have to perform? At least tell me the step. I'll write down the things by myself. X to the power minus 2 is there. So how do you integrate it? X to the power n is there. How do you integrate it? Yeah, Jesslyn, you're answering? Are you typing? X to the power n is there, then how do we integrate? We write this as nx to the power. See, when you are integrating, x to the power n is there. You add 1 to its power, you divide by the same. So if it is x to the power minus 2, so minus 2 plus 1 here, divided by minus 2 plus 1, and you put the limits from infinity to R. So what is left? Minus K capital Q small q. This is x to the power minus 1 divided by minus 1 from infinity to R. Now look, this minus will automatically make it positive. So K capital Q small q. X to the power 1 minus 1 is coming. Let's make it as 1 by x from infinity to R. Let's put the limits now. So see, this will be K capital Q small q 1 by R minus 1 by infinity. What is 1 by infinity? Infinite.
Ma'am, not defined. Can neglect it.
Now 0, right? Just it is 0. 1 by infinity is 0 and 1 by 0 is also infinity. So here this part becomes 0. So what is the formula of the work done? K capital Q small q divided by R. Now what did we discuss? We discussed the formula of potential is work done divided by the charge. So work done is K capital Q small q. This is Q. Q gets cancelled. Potential is K capital Q by R. or K's value we already know. K is equal to 1 over 4 pi epsilon naught. So V is equal to Q by 4 pi epsilon naught. Now, potential is not a vector quantity, it's a scalar quantity. You've written just before this. So if it is scalar, for positive potentials, you are going to take this as positive only. Negative potential, take it as negative. Here, you don't have to take the magnitude of the charges. In electric field, electric fault, constantly I was telling you, take the magnitude of the charges. Right now, you just have to take the charges as it is, because it's a scalar quantity, and add and subtract it directly. So this will be positive if the charge is positive. This will be negative if the charge is negative. So formula is KQ by R. See, when you had force formula was F is equal to KQ1 Q2 by R square. F is equal to KQ square by R square if charges were same. Electric field was KQ by R square. Now potential is KQ by R. Is this derivation clear to both of you?
Yes, ma'am.
Jasleen, what about you? Anything you want to ask? I hope it's properly clear, Ibrahim. You're understanding properly?
Mm-hmm. Yes, yes.
Okay. If you want to ask anything, then just ask in between. Okay, just C class, this derivation is one of the important derivations for your board exams. This derivation often comes in the exam, and in your school exams also, you'll find this derivation for potential especially. Not electric field due to a point charge, but potential due to a point charge is often asked. So, okay, please start writing this. See now, look at, I hope you've written. Are you still writing?
Ma'am, I wrote.
Okay. Jasleen has also written. See, this is the formula of electric potential due to a point charge. So let us calculate this. Here the charge is given and separation is given, and you are asked to calculate the potential at this point. So see, the formula of the potential is K Q by R. This is the formula of it, K Q by R. Now, K, we already know it is 9 into 10 to the power 9. Ibrahim, can you tell me what is the value of charge which should be put here?
Ma'am, +3 as normal 3 into 10 power minus 2, yeah.
Why positive 3?
Ma'am, because it's charged, so it's not, it won't be a vector, it will be just a scalar.
Charge is
Charge
a
is
scalar, your
scalar.
potential is a scalar. So see, what did I tell you
Mm-hmm.
before this? When you have a positive charge, it can be positive, and when it is negative, it can be, you can put the charge exactly as negative. So if the charge is, see, this concept which you are answering is valid for your electrical forces and electrical field. There, those quantities are vectors. So you have a separate parallelogram law to solve its magnitude and get its direction. So that's why we always take the magnitude over there. But right now it's a scalar. There is no other method to solve it apart from your simple algebra. So you have to put this as multiplied to minus 3 into 10 to the power minus. Okay, is that clear?
Yes,
Yes.
ma'am.
Okay. Separation is 9 millimeters. So 9 into 10 to the power minus 3. So 9 gets cancelled. This gets cancelled. Potential comes out to be minus 3 into 10 to the power 9 volts. So see, this is a negative potential depicting that it's a negative charge. That's nothing. Okay, quickly write down this and just text me a done once completed. See, when you have n number of point charges present, so when you're calculating the electric potential for n number of point charges, here it is very easy to calculate it. See, let's say this is a common point P, and at this common point P, you are trying to get the net potential due to various charges that are present. So at this point P, there will be a potential due to Q1, there will be a potential due to Q2, Q3, Q4, like this nth number of charges are present. So what do? You add the individual, you calculate the individual potentials first. V1, V2, V3, like this, you will calculate the individual potentials first. When this is calculated, all the different individual potentials are calculated, then the net potential will be simply the sum of all the potentials, V1 plus V2 plus V3 plus V4 up till Vn. This will be the net potential. And it will simply, because see, this is just your scalar addition. Okay, this is your scalar addition. So what does the rule say? Rule says that for a system of n interacting point charges, electric potential at a point is algebraic sum of potential due to individual charges. This is the superposition principle. But just one thing here is different, that vector addition is not there. It's the algebraic sum. This is important. It's the algebraic sum here in this particular case. And okay, write it till here, class. Write down this one. Look, class. Now, see, when you have the formula of V as work done divided by charge. So here, when you are calculating the work done will be charge multiplied to the change in potential. Why change in potential? Because you have 2 points and you are calculating the points due to both of these. Suppose this is B point, this is A point. You're bringing this charge from A point to B point. A is VA, B is VB. So when you're bringing this charge Q from A point to B point, this is also having its potential at its place. This is also having its potential. So work done is Q into VB minus VA. Now see, when this one of the initial points is 0, then only we have infinity. See, suppose VA is at infinity, then only see our definition is suitable work done divided by charge. But when both the points are there, that means potential difference is there. Initial and final points are present. Then you write the formula as work done is charge multiplied by the difference of the potentials. Like look at this question. This is a question saying work done by external force in carrying electron from A to B. So work done is charge into V final minus V initial. This is the formula. Charge due to electron is 1.6 into 10 to the power minus 19 coulomb. Final potential is from A to B, means minus 20, then minus, then this 10. So look, this comes out to be minus 30 E, right? E, I'm just writing for it, electrical. This is the value for it. So just quickly copy it. Class, just let me know once this is completed.